Hey DerbyCon, if you're watching this video, it means that my wife is giving birth to our third child, which, while I'm sad I'm not down there with you guys, I wouldn't miss the delivery for the world. I hope you guys can understand. So, I'm Liam Randall, and I'm primarily here to represent the blue side, the defensive side of this talk. I have a CS degree and cut my teeth doing large-scale network administration. I've been consulting for the last 10 years and have spent the last few focusing specifically on IR. I've been consulting for the last 10 years and have spent the past few years focusing specifically on incident response. If you've met me personally, you'll already know that I have a real passion for open source software and found a home on the Bro Core team. This year, especially, Bro became my full-time job and I'm currently working on product development. I spend a lot of time teaching people about Bro, putting on workshops and training. I'm teaching a half dozen classes still remaining this year. If you're interested, please check out my blog at liamrandall.com. I got involved in this talk specifically because I have a real interest in advanced red team tactics. The stuff that Kyle does really scares the crap out of me. He's out there developing new and novel approaches to penetration testing. From my point of view, it's harder to defend against things you don't truly understand. So let's pick up right where Kyle left off. By this point, you should start to pick out on what we're trying to communicate today. It's that ICS embedded systems are really soft targets. And while there are dozens of distinct methods of attacking and exploiting these devices, we're just trying to demonstrate a couple. The ultimate message is that all of these things you're already doing on the PC side work with only minor modifications in this space. Your entire arsenal can be deployed. So we've been pretty deliberate about our target selection and exploit vector. We took down a SCADA controller with an ICS protocol bug over TCP/IP. We took down a common key set via serial interface attack, something that requires you to be physically present. For this next one, we're going to do something a little more common, somewhat pedestrian, but a more persistent and prevalent vulnerability: default credentials. So before we move on to the defense side, let's run through just one more example. This time we're going to use default credentials to attack a common brand of PTZ camera. Okay, so on to our target. There are lots of models and manufacturers to choose from. I chose the Sony PTZ because it's a relatively high-end brand with a very large deployment footprint. I spent a little time researching and I found absolutely no record of the technique that I'm about to demonstrate for you published anywhere. Now, default credentials are certainly not a 0-day. However, I'm going to demonstrate how easy it is to build and upload a Trojan firmware for one of these devices. Okay, so onto the device itself. Let's take a look at this guy. So it's got built-in Ethernet. It can have optional Wi-Fi, a couple expansion slots to add a memory on it. As far as protocols, it speaks the regular TCP/IP suite. It only has 8 megabytes of memory on board because this is one of their older models. It has is on the camera side, it's got 25 times optical zoom, multiple frame rates and codecs, and then the camera actually supports any little interface model on the back. So it's kind of a camera ICS controller at once. It has alarm inputs as well as a couple serial interfaces. So these things are commonly set up to do things like buzz open gates or doors or key on pressure sensors or things like that. They're great. There are a lot of new models in this series, but this one's fine. So let's take a walk through how the firmware in this device is updated. So again, the what we're starting with today is finding a device that has default credentials. So the first thing you do is simply authenticate to the device. Then, checking the IP, you can use the CGI commands to remotely turn the FTP server on or off. So if I wanted to upload my payload, I would obviously turn that on. I then FTP to the device and create a web home directory and upload whatever I want the device to end up with. I go ahead and push my resources up, and then I make another CGI call, and then boom, I own this camera. So the technique that we're about to demonstrate, I'm just going to upload a payload that I generated using the social engineering toolkit. However, we could easily use the techniques that Kyle just demonstrated to build custom executables for this device or a myriad of other techniques. So what I've done here is I've already logged on to a camera here on a local subnet, 192.168.0.236. This is a PTZ camera, and since the camera itself runs a little slow, I've already uploaded this web directory to the camera. So if we take a look at what I have in the web directory, what I've done is I've copied the existing firmware so the camera will continue to function as far as the Java controls for viewing images and so forth. And then I also created a new subdirectory called set payload where I've just done a simple a Java-based website attack. So let's go ahead and browse out to the camera itself and take a look at what this thing looks like. Okay, so up in a browser here, I have the Sony PTZ already loaded, and we could log on and browse. Looks like I have a HTML error in the firmware that I've uploaded, but not a big deal. We can still see images off this camera. Uh, and we can also browse directly to this camera itself. And you'll see that I'm launching a Java attack against this user. Now, this is a relatively unsophisticated attack. What I could do is actually edit the default HTML files that come with this camera and build something right into the default homepage, which would I think be a very sophisticated attack because these cameras do prompt you themselves to run Java utilities and so forth. So if this were a real attack, I would go ahead and launch that, and now I would have connected back to my instance of Kali here, and the system would be pwned. So the greater technique here that I'm attempting to demonstrate is simply that these cameras in these embedded devices are a platform that you can use to pivot throughout the rest of the infrastructure. Okay, so what's the big deal? So we've had three demonstrations today so far that kind of go into some more advanced red team tactics. Do these things really matter in the real world? Are these things that you need to be concerned about in your environment? And this is where the story takes a very interesting twist and why I think that we're going to demonstrate very quickly that this is a real thing to be concerned about. In early 2012, there was a study that was released that was called the Karna Botnet, or the Great Internet Census of 2012. Internally, a team out at Lawrence Berkeley National Lab referred to it as the alien worm. There is a very bright group of individuals out there, and an especially bright individual named Shish Sharma, works on an incredible team of incident responders. He's a Bro Power user, and he's been involved so far with the discovery of a large number of network anomalies. Some that he's talked about publicly are the 2011 Mordo worm, the 2012 alien worm that we're about to review, and the 2012 MySQL authentication bypass vulnerability. Uh, Ashish runs a very large Bro cluster, and he uses it as a network telescope to basically get some insight into trends that are going on network wide. So if you haven't read about the Karna botnet, the paper they put up is wonderful. I highly suggest you read about it. But let's just read how they describe the worm themselves. So the first thing is access. How were they accessing these embedded devices? And they note that we discovered an amazing number of open embedded devices on the internet. Many of them are based on Linux and allow logon to standard BusyBox with empty or default credentials. The scope was insecure devices are basically located everywhere in the internet. They're not specific to one ISP or country. So the problem of empty or default passwords is an industry-wide phenomenon. In the deployment that they performed, they compromised 25% of the devices they found. Approximately 420,000 unique devices were compromised in this one worm. And then as far as a payload, the binary in the router was written in plain C. It was compiled for 9 different architectures using the OpenWRT build root. Its latest and largest version, this binary was between 46 and 60 kilobytes in size, depending on the target architecture. And then they use these binary to actually scan the internet. They actually tried to scan /0, and you can download all the results if you're interested in seeing what a snapshot of the full internet looked like at the time. They were pretty sophisticated when they conducted their scanning. They tried to go in low and slow. Each device would only scan a couple of IP addresses each and a couple of ports. So let's take a look at the payload itself. So this is a directory listing of a compromised device. Now this is just a sample. We believe that there were multiple revisions, and there would obviously be some minor differences between the 9 unique architecture that they targeted. For the device that this was captured off of, the default password for this family of cameras is either root and blank or root and 123456. The Linux itself reported back as High Linux BusyBox. Um, the total payload is just a little less than 4K with the scanning and the logs there. This file barm underscore v6k was the daemon that would spin up and run on TCP port 2010. And there were some other indications of this worm when this botnet when it first started operating. If you check just isc.sans.edu, the Internet Storm Center, you can see some evidence of this activity running around the internet. And again, these were a custom payload. Uh, Based on the research that Ashish had performed, this sample was taken on June 28th, 2012, and looking back into his network, he saw activity back through May 30th of 2012. So if you notice, there was a README file installed on the payload, and here's what the README actually said. Your router had a very simple or no telnet password at all. We temporarily use it for a nonprofit research project to map the internet. All research results will be made public. We have no intent to damage your device or harm your privacy in any way. So, and then they listed an email address to contact them if you'd like. And if you guys are here, the guys that perform that, I think you'd be pretty easy to pick out. You'd be the guys walking funny because you have balls the size of footballs, considering the number of devices that you guys actually compromised. Okay, so let's take a quick look at the devices themselves. And I think this is where we really start to tie everything together. OpenWRT build root was used via default credentials to build a gigantic botnet to scan the entire internet. Dozens of vulnerable models were actually infected during the course of this botnet. And if you consider where cameras are deployed to begin with, they're already typically in your sensitive areas because it's where you want some kind of physical security. It could be behind your firewall. In the initial research into this botnet, there was a very scary moment when all of the production was traced back to a single Chinese OEM. Now, initially, that was very concerning, but I think later, as the worm evolved and stayed relatively benign, people began to realize that it was just a systematic problem in the design of the devices. And these are the super inexpensive home security systems, small business security systems that you see deployed everywhere. Uh, you may have one of these at your house now. You buy these at Amazon.com, on Costco, Sam's Club, hundreds of retailers online. And a picture is worth 420,000 devices. It's actually kind of beautiful when you look at it like this. And this graphic here was actually generated by the Karna botnet team. Let's consider here a little ASN analysis. So ASNs are autonomous system numbers. Those are the numbers that are given to the networks that make up the internet itself. So 25% of these infections were on one single network, and that would be this big red area you can see over here in China. They were connected to China Telecom. And if you count the top 5 ASNs that the cameras were connected for, that accounted for approximately 50% of these cameras, or 210,000 devices. And these were primarily Asian ISPs, with the exception of Turk Telecom here. Another hotspot of inexpensive Chinese cameras. But there was a really, really long tail of infection. If you look at the map of the Karna botnet, it generally reflects a map of the United States with a slight Asian, or a map of the global internet with a slight Asian bias here. The top 16 ASNs only accounted for 60% of infections. Ultimately, these inexpensive cameras are available anywhere, everywhere, and they're deployed everywhere. I mean, you can even see these hotspots down in South America here. If you have an opportunity, pull up the paper. It is very interesting. Okay, so what does all this mean? These are systematic vulnerabilities. These are pervasive throughout the internet, and they go way beyond just cameras and ICS. They affect almost every embedded device. If you follow this space, you'll find that there are vulnerabilities in copying machines, in all of the Internet of Things that we're putting out here. These are not just theoretical attacks. As the Karna botnet shows, there are sophisticated operators that recognize the opportunity and are taking advantage now. The tool chain has essentially evolved to a level where it is now a trivial effort to port all of our existing uh, tactics, tools, and procedures to the embedded ICS space. And unfortunately, that means that this is a problem that we all need to mitigate. So, how do we find this stuff? When we're talking about ICS and embedded world, these are defensively handicapped products to begin with. When we talk about finding this stuff, I think generically we mean we want to find bad stuff, but let's first also consider how we find stuff in general in this space. And the sad reality is that the traditional techniques that we've been trained on just do not meet the needs of the embedded ICS world. When you consider the things that you may do in your network now, you may conduct a little network scanning. A lot of times you will be specifically excluded from scanning, things like your medical resources or your power control or water control equipment because you don't want to take it down. Um, Patch management programs for these things are non-existent. You're lucky to get semi-regular firmware updates, never mind having something like SCCM or a management utility that can help you. You rarely have access to the system logs in these devices. At best, you might have syslog, but sometimes they're just very difficult to configure. There's no AV that runs on these things. There's no host-based intrusion detection systems that can help to alert you. Again, things like Nessus and Nmap, the scanners are wonderful. They do include sometimes routines for mapping these devices out. But a lot of times you don't have that second step, that logon agent that then logs into the device and queries it for local vulnerabilities or problems. Signatures can be effective. There is a wonderful project called Digital Bond that specifically addresses some of the worst in the ICS space. So an area that we can kind of turn to. Flow data is an area that is very helpful because it helps you to understand, the kind of ground truth of what's going on in your network. And then there's always segmentation. Uh, but the TLDR is that most of these techniques just don't work any longer. So when we consider traditional intrusion detection systems, let's take a step back and just look at it from a very high level. Classically speaking, if you read the academic literature, if you study this professionally, you'll find that usually IDSs are broken down into two distinct and separate categories. You've got your signature-based IDSs and your anomaly-based IDSs. Your signature-based detection are the things that you typically think about. This would be like snort rules or atomic indicators of bad things, bad domains, bad file hashes, bad IPv4, v6 addresses, and so forth. Anomaly detection is defined somewhat differently depending on where you check, but I think that it generally means that you're going to use things like traffic analysis, flow analysis, and protocol analysis with a little bit of magic and special sauce to sort of determine when things are different on your network. So the system that I spend a lot of time working on is called the Bro platform. And it is essentially a hybrid platform that offers the best of both worlds. But more importantly, it includes this very powerful programming language that is what really separates it from everything else that seems to be out on the market today. Um, and we really try to focus on that area where we can kind of bring together all of this unique intelligence. So seriously, so what is Bro? So Bro is three things, and it does three things. So when we talk about what Bro is, we talk about first there is this Bro platform, and that would be the utilities and the APIs and all the management stuff you need to get it up and going. The second thing that Bro is a programming language. It is a Turing-complete programming language. It is event-based. Syntactically, it looks a little bit like Python. And it's a very easy high-level language to work with. You never worry about, cluster safe anything. It's all sort of embedded and taken care of in the language for you, regardless of the size of the network that you're programming for. And then there are applications that run on the Bro platform that are written in the Bro programming language. So the first big application that people talk about and sometimes mean when they say Bro is just Bro IDS. And we'll look at what Bro IDS does in just a minute. But other applications also include use cases for network monitoring, vulnerability management, DLP, traffic analysis, file analysis. And in reality, the thing to keep in mind is that all of these apps are really just Bro scripts written in the Bro programming language. So Bro is three things. It does three things. The first thing it does is it writes. Actually, before we talk about what it does, let's look at what Bro looks like on the network. So Bro takes a passive feed of all traffic on the network. So it doesn't matter what the device looks like on the other side. It doesn't matter if it's an ICS controller or a camera or a Polycom IP phone or a server or a tablet. If it's speaking TCP/IP and it transits the tap that Bro's listening to, then Bro understands it and can statefully track and follow that conversation. Uh, it gives you then access to all the layers of that traffic. If you think about the TCP/IP cake, if you will, you have access to all those different layers as you interface with the traffic, and you can do things. So the first thing that Bro does is it writes these very, very rich protocol logs. You get one of these protocol logs for each protocol that Bro is decapsulating, plus a bunch of extra logs as you see fit. Bro is very, very easy to customize. So the idea is that you can even append things onto the existing logs, like geo-IP information or ASN databases or atomic indicators of intelligence, things like that. If you're Unixy, you would love Bro logs. They're very highly structured. So when we say highly structured, we mean here what I've done to help you kind of understand that is I've put the data type under the field name here for each one. So count is the Bro word for integer. So you know that everything in this column, if you want to access it using the Bro programming language, is always going to be an integer. This is always going to be a string. And so Bro will alert you to things. Bro IDS comes pre-configured with a variety of signatures and an anomaly notifications, and we can look into more on that later. And then there's the most exciting part about Bro, which is that programming language. So this is that real power that lets you take all the things that are in Bro and that Bro has access to and pivot. So what we're going to do is we're going to look at using these hybrid anomaly and signature based detection systems to sort of look at what's going on the network. So how do we start to defend these ICS systems? You know, we've kind of looked at a variety of these attacks today. How do we stop these things from happening? And I think that we need to begin with, understanding what you have. You know, what does network monitoring look like when you're looking at these systems? You know, the Socratic ideal was to know thyself. So let's look at this camera here. So this is a graph of traffic. Um, where green is HTTP traffic. So if I just browse to this that Sony PTZ camera we looked at, and I open up and I start looking at the stream, this is what I see on the network. just HTTP traffic. Now, the attack that we executed on this, where we uploaded our own firmware, obviously looks completely different. Here we're seeing FTP traffic and FTP data. So these are the kind of things that you should start to monitor for in your network. Is your network supposed to look like A or B here? These are easy things that when you look at them make sense, and you can use a system like Bro to use a simple if statement to do some things like protocol pinning. So looking at that Bro connection log that we were talking about a few minutes ago, here's another perspective on that ground truth. Um, just monitoring for every network connection that we saw there were 14 HTTP connections in that normal traffic when we just saw that green line. Whereas in the second graph where we saw the purple and the red for FTP and FTP data, we see there was a significant amount of other traffic. So helpfully, the greater idea that you may want to know about your network is simply when do I have new services appear on my network? Do I have a new FTP server startup somewhere? Do I have a new HTTP server startup somewhere? Is a server now speaking SSL that wasn't before? And very helpfully, Bro will write a single log line for very helpfully, Bro will write a single log line for each new service that appears in the logs when it appears. So even just hooking this log and having Bro email you daily or hourly or immediate summaries of results for when these things are turned on can be very instructive. So digging deeper into the protocols themselves, though, you're not limited to just traditional NetFlow type records where you're just saying like, oh well, I'm going to limit based on a certain number of ports or even on a protocol. Bro does dynamic protocol detection, so we put all the HTTP in there, and then if you want to care about what port it was running on, you can care about it. In this case, what I'm highlighting is that that if you know thyself well enough, or if it's an application that is important enough, you can even pin and have Bro alert on things like the URIs that were accessed or the number of times that URIs were accessed. You have this new range of detection methodologies at your fingertips that really empower you as the security professional to enforce policies in a way that you just can't do with another system. So let's take a step back real quick and make sure that we understand something about Modbus because we're going to kind of dig deeper into a more complicated device and look at how we can secure it using these new tools and programming languages on our network. So if you're not that familiar with Modbus, Modbus is a very old serial communications protocol that's now used and implemented over TCP/IP and has been for quite some time to connect these large devices or networks of discrete devices around. So where you find these things are in big, expensive devices with capital life cycles. So think like power plants, think about water treatment plants, think about assembly lines, oil and transportation, maritime, military, fracking. These RTUs, remote terminal units, are what you use to connect to things like humidity or temperature or flow or pressure sensors, and they essentially can be pre-programmed to tell you to just read in some sort of take a reading and then pass it back to the SCADA network. The SCADA is the supervisory control and data acquisition side of the network. That's the stuff up here. And these SCADA controllers are what sort of interpret the logic of the device. If you look at the protocols themselves, and we will in just a minute, you'll see that the protocols themselves need context to really understand what's going on there. So just as we were looking at the con.log and the http.log, Bro includes some SCADA protocol analyzers. So the 0-day that Kyle popped earlier was on a protocol that is not as common. It's called 6NAT, but the two most common are called Modbus, and the second most common is DNP3. And the way that these networks work are you'll have a number of these devices here, and these devices can communicate as sort of masters and slaves. So Out of the box, there are scripts here that give you that deep intelligence into your network. So you could say, is it normal to have these new devices acting as masters on my network? Now, you're obviously going to need to know something about the network to enforce these kinds of things. But where SCADA devices are usually installed are these sort of expensive, higher order devices where it would be worth it because you're trying to protect some kind of critical infrastructure or assets. So just as with HTTP, we were digging deeper into the protocol itself and looking at some of the logic inside it. We have similar access to Modbus. Here we're just talking about what is actually being done on the registers itself, but we can actually even dig in one step deeper if you're familiar with the logic and actually pull the registers off the Modbus, out of the Modbus protocol in real time. Now, this would require some real sophisticated knowledge of what these registers stood for. You'd want to know that that register 8002, what this current value, I'm sorry, what register 6352, what a jump from 8000 to 13,000 actually means. Is that relevant or statistically significant in your network? Mining the logs out of a couple of these registers, a team member at the International Computer Science Institute was able to generate this graph of SCADA register changes over time. And you can see here that this blue line could be something like a pressure switch or a valve switch, and maybe this is the impedance of some circuit here, so maybe it's measuring a tank that's getting full. I have no idea. But that's actually a great thing to say because I have no idea what these things actually represent. However, if you do know what they should represent, or if you are aware of what normal operating ranges are for a particular power plant, or a phase change on a device, or when certain sensors should be open and not, you could detect things like advanced attacks within your infrastructure. I'd like to talk more about this, and I will be actually talking about this in somewhat detail at MIRCON, but today I just don't think we have time to go into the nitty-gritty details.